Good morning, and welcome back to Chapter 3 of Knots and Links, read by me. Chapter 3, The Fundamental Group. We are now interested in knots and links of codimension 2, which includes the classical case of s to the 1 prime s in r to the 3 or s to the 3. The most successful tool by far, in this setting, is the fundamental group of the complement. This chapter discusses various applications of that tool. Section A. Knot and link invariants. A knot invariant is a function k f to the k, which assigns to each knot k an object f to the k in such a way that knots of the same type are assigned equivalent objects. Similarly for links. One hopes that f to the k is reasonable to calculate and, on the other hand, sensitive enough to solve the problem at hand. For a one-dimensional link in 3 space, certain numerical invariants have been found useful. We will discuss most of these in subsequent chapters, but the linking numbers measure the number of times each pair of components wrap about each other in an algebraic sense. This is a natural generalization of the index of a curve in the complex plane about a point. They are easy to compute, but only give a first-order description of the nature of the link. Crossing number is the minimal number of self-intersections which appear in a planar picture or regular projection of a link or knot of a given type. This simple measure of complexity has been used to order knots in the various existing tables, including the one in Appendix C of this book. That sounds important, so I'm going to just read that all, again. Okay, excuse me. For a one-dimensional link in 3 space, certain numerical invariants have been found useful. We'll find most of these in subsequent chapters. Linking numbers measure the number of times each pair of components wrap about each other in an algebraic sense. So the linking numbers is a good thing for me to write down if I had a pen, which I don't. This is a natural generalization of the index of a curve on the complex plane about a point. Cool. They're easy to compute, but only give a first-order description of the nature of the link. Okay, so linking numbers are the first order, and they measure the number of times they wrap, which is a good thing to measure, in a algebraic sense. I don't know what, wrapping I'm necessarily thinking of. It might not be the algebraic sense, so if you're thinking in the algebraic sense, good for you. Maybe we'll come back to that and see if I can figure out what that means specifically. The crossing number is the minimal number of simple self-intersections which appear in the planar picture. Oh, yeah. Oh, and then I think these planar pictures are like these ones back here, so it's something on here? Because this is definitely Appendix C. And there's definitely wrapping amongst oneself, so there's like that, and it's like this one definitely wraps amongst itself, so that's possibly the crossing number. Whoa, so is it like one of these? Okay, well, it's probably not 21. And here's, maybe it crosses backwards and then forwards 3 times and then backwards 3 times? That maybe, or maybe it crosses twice? Okay, this is links and not knots. I've been working on this first page, and I got up to, I think that last one I did was 7 sub 2. So there's 55 or 52 or 52, 7 and 2 and 5. Yeah. So one of those is the crossing number and one is the linking number maybe. So we'll work that out. This simple measure of complexity has been used to order the knots in the various existing tables. Oh, hey, I think I know what's going on. So I was doodling around in here and looking at these. So this goes 3, 4, 5, 5, 6, 6, 6, 7, 7, and then there's I think 7 of the 7s, and then looks like 16 of the 20. Oh, lots of 8s, 21 8s, and presumably lots of 9s. So I'm guessing this is the index number. Because this clearly has 5 somethings, and this clearly has 3 somethings. This one is certainly 4 in some way. So yeah, once you get to the 5, you get 2 of the 5s, and then you get 3 of the 6s. And, I think it might be like a Fibonacci something or other. How many 8s were there? I don't remember. Anyways, 7 clearly. But then there seems to be some sort of crossing to be numbered. Well, this simple measure of complexity has been used to order knots in the various existing tables. So the crossing number is the minimal number of self-intersections which appear in the planar picture of a link or knot of a given type. Yeah. I should really put a bookmark here. So how many crossings? Oh, does that cross 3 times? That crosses 3 times. That crosses 1, 2, 3, 4. That crosses 4 times. That clearly crosses 5 times. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Oh my golly. So how many times it crosses over is the crossing number, and the linking number. I wonder if this is the sub is the linking number. I would have put the bigger one first, but I also don't know what I'm doing. Crossing number is the minimum number of self-intersections which appear in a planar picture, regular picture of a link or knot of given type. Well, let's... Oh god, there's more numbers. The minimax number is... Oh god. The minimax number is the smallest number of local maxima or minima of a knot, K, such that S1 R3 in a fixed direction where K ranges over a given knot type. Milnor has studied this in relation to total curvature of a knot in a beautiful little paper in 1950. sounds like a delight to look into sometime. The genus of a link L is the number of handles on a minimal service in R3 spanning L, and has generalizations to some higher dimensional knots and links. Torsion numbers, Minkowski units, signature are and some other numerical invariants are more difficult to describe without some preliminaries, but also play a role in answering certain questions about knots. We shall also encounter polynomial invariants, the Alexander polynomials, matrix invariants, quadratic forms, etc., which are, in a sense, just glorified numerical invariants. The complement R to the n minus L of the link L is clearly an invariant up to homeomorphism type, i.e. a topological invariant. Whether this is a complete knot invariant, even for classical knots, remains at this writing an open question which has received much attention and partial solution. See section 10i. It's also 2018, so who knows? That could be a fun extra credit question to anyone who wants to tell me in the comments below. 1. Conjecture. If two tame knots in R to the 3 have homeomorphic complements, then the knots have the same type. So if you were at a cocktail party and somebody said,